we have this situation Okay, so we take this patient, right, and we put them in like that. Okay, so we slide the patient in the scanner. Right? When he was out here, all of the protons and all of the water throughout his tissue each had some unit of nuclear magnetism, and they were all randomly oriented. We place the patient in the scanner, right, under the influence of some strong externally applied magnetic field, and the magnetization of our patient looks like that. And then we go through this procedure where we turn on our B1, our RF, tilt this magnetization into the transverse plane, and listen for that signal at some point that we choose, called TE, as the signal is relaxing or going away. And the signal amplitude changes over time, and that signal amplitude is essentially, not essentially, it is a measure of how much transverse magnetization we have. And we choose some point TE to measure it at. Okay? So when I do that, and I get some measurement of signal amplitude, we have y units of signal amplitude, whatever it happens to be. So where does that signal come from? Anyone?
Body.
Right, okay. So if we make things easy, we'll say that the coil that we're using to sample this signal looks like that, okay? And basically, it is sensitive to whatever magnetization might be precessing in the transverse plane anywhere in the bore of this scanner. This isn't such a good real-life example, but it makes things easy for us. So in this case, the signal that we detect, right, comes from all of the spins, all of the water protons, anywhere in the body. And it's essentially a summation of all of that signal. We have absolutely no way of telling how much of it comes from the brain, or the heart, or the liver, or the toes, or wherever. It's coming from everywhere. And that's really not such a useful piece of information. Right? It certainly doesn't allow us to make any assessment of the question we started out with yesterday. If you're looking at the liver and there's a tumor in the liver, how can you possibly distinguish them? Because this signal will be some average of everything. I mean, at most, if you had something bad going on that was a big enough component of the signal in that patient, you might be able to tell in general that there was something bad someplace in the body. But it wouldn't really give you much in the way of diagnostic information. So what we need to do is to generate an image. And the way we're going to go about doing this, right, so most of you are familiar with the fact that when I talk about an image, that it is a 2D, right, array of pixels. And we can talk about it as having, x and y dimensions. But the images also, as we'll see, actually have some thickness. So even when we look at these supposedly two-dimensional images, you have to realize, even when you look at your CAT scan or your ultrasound or whatever it is, it's not some, infinitely thin slice. That slice has some thickness to it. And each of these pixels that we're talking about, we actually call these voxels for volume elements, because they're not just a representation of some 2D location, but they actually are some 3D chunk of tissue. So what we're looking to do is to generate an image like this, which is a two-dimensional array of a bunch of little prisms, each one containing information about some volume of tissue. And of course, the size of these voxels and the number that we have arrayed across the dimensions of the image is going to determine the spatial resolution of our image. So in order to approach this, we're going to take a stepwise approach, which is the first thing we're going to do is try and simply select information from a single slice. And then followed by that, we are going to address in sequence localization in the plane of that slice. Okay? And these are essentially three different components of spatial localization. Right. The easiest one has to do with slice selection. And hopefully we'll dispense with that relatively quickly this morning. Right. The in-plane localization of signal uses two techniques, right? One is called frequency encoding, and the other one is called phase encoding. Right? Those terms are probably familiar with you, familiar to most. Has anyone heard of frequency and phase encoding? Who has? Raise your hand. Okay, a lot of people. How many people think they understand how you localize a signal in the image? Even have some vague idea. Be forthright. A couple of people? Okay. By the end of today, you will be experts. All right. So let's start with identifying a slice. So here's our patient lying in the scanner. I left the scanner out just to make things simpler. And we have our static magnetic field, B naught. So in the presence of this homogeneous static magnetic field, we just said that if we tilt the magnetization in the patient into the transverse plane, that we are going to be detecting signal from the entire body. Now, what did it take to make this magnetization tip into that transverse plane? Right. In order to do this, what did we have to do? We had to turn on our RF at the Larmor frequency, the precessional frequency that corresponds to whatever our magnetic field strength is, which in the case of B naught, that's the Larmor frequency, omega naught. So let's change the situation a little bit. And what I'm going to do is to turn on a gradient magnetic field. So this gradient magnetic field I'll show as a line that is changing from foot to head. What this means is that if I were to plot over the z distance the gradient strength, right? The gradient would be lower amplitude down by the feet and higher amplitude up at the head. Now, as we discussed yesterday in talking about some of these hardware issues, there's some location in the scanner called the isocenter of the scanner. And that at that location, gradient amplitude will always be 0. Right? Because remember, this Z gradient magnetic field, which we discussed yesterday, is generated by two electromagnets, one at each end, which have equal and opposite magnitudes. So those vectors become smaller and smaller as you get to isocenter, at which point they are equal and opposite and essentially cancel out. So what we actually have is a range of gradient strength, which is negative and positive, depending on which side of isocenter we are on. Now, this is just the gradient magnetic field. Well, in addition to this, we have our static magnetic field, B naught. And if we take that into account, we can actually plot, again along the z direction, the net magnetic field strength, which at isocenter, and let's say that this net magnetic field strength is going to range from B0 to B0 plus G and B0 minus G. Okay. At isocenter, the gradient magnetic field strength is 0. The net magnetic field strength is the sum of all of the magnetic fields that are present in the scanner, which include our static magnetic field strength that is homogeneous all the way from left to right, and whatever gradient magnetic field strength might be present. Of course, the strength of the gradient magnetic field varies depending on location. At isocenter, there is 0 gradient magnetic field strength. So the net magnetic field strength is simply B naught. As we move to the right, we have this positive gradient magnetic field strength added to B naught, and we get progressively stronger. Whereas we go to the left, we get progressively weaker. So what happens in the presence of this gradient magnetic field is that there is a variability of the magnetic field strength experienced by spins as we move from foot to head and vice versa. Okay, is that clear? Because at this point I'm just reviewing the nature of this gradient magnetic field and what it does.
What creates it?
What creates it is 2 electromagnets, right? One at each end. Basically, right, to be simple, a coil of wire with some current running through it that generates a magnetic field that looks like that. And another one over here with a coil with current going in the opposite direction generates a magnetic field that looks like that.
And
So,
this is regardless if you're just scanning the head or just the abdomen.
well, these are built in to the main piece of hardware that's sitting there in your room. So that if you go inside the bore of the magnet and you start to peel away the layers on the inside, this is one of the things that's built into the inside of the bore. These coils have nothing to do with the receiver coils that we use for detecting the signal. These are specifically to generate these gradient magnetic fields. Okay? Unlike the static magnetic field, which is always on and is perfectly homogeneous, these gradient magnetic fields are not always on. They're only on during imaging, and they're only on during certain times when you're imaging. We're going to talk about that more tomorrow, or a little bit today. Okay? So this is the nature of the net magnetic field strength as we go up and down along the length of the bore of the magnet. So in the presence of this gradient magnetic field, if we do the same thing, you guys have a question?
Yeah, why is there a 0 in the z-axis? What does that represent?
What does this 0 mean?
Yeah.
This is the isocenter.
Just, it's not the 0, the actual value of the 0 is the value.
This is a location along Z. So instead of measuring from 0 to 100 centimeters, let's say, I'm going from minus 50 to 0 to plus 50. It's really arbitrary. I used 0 because of this concept of the isocenter of the scanner, which is important to keep in mind. And also, in real life, the way the vendors generally set things up, they talk about distance inside the bore of the magnet as being plus or minus relative to the isocenter of the scanner. Okay? But in a sense, it's arbitrary. Yeah. Okay. So if we do the same thing again, turn on our RF at omega naught to rotate this magnetization, but we do it in the presence of this gradient magnetic field, what happens? Well, we do that, and we generate some signal, right? And then at TE, we measure that signal. So my real question is the signal amplitude that we measure at TE, right, however many units of signal amplitude, where does that come from? Where is that signal arising from? Someone said tissue.
Isocenter.
From the isocenter. Okay? So remember, to generate the signal, we turn on our B1, which is a rotating magnetic field, right? It rotates around perpendicular to the bore of the scanner at the Larmor frequency. As a result, it efficiently transfers energy onto spins that are precessing at that Larmor frequency. Resonance only exists where there's a match between the frequency of rotation of the RF and the frequency of precession of the spins, right? If we have spins that for whatever reason are precessing at a different frequency, there's no resonance, there's no efficient transfer of energy, and there's going to be no flip of that magnetization, right? Choosing this frequency at which we transmit the RF is essential. Under the influence of this gradient magnetic field, spins at the isocenter experience the static magnetic field strength B0, but no gradient magnetic field strength, because by definition the gradient magnetic field strength is 0 at this location. Since they experience the field strength that matches the frequency at which we are transmitting our RF, they receive that efficient transfer of energy and they are rotated into the transverse plane. But in the presence of the gradient magnetic field, anything north or south of isocenter is subject to a different net magnetic field strength. Therefore, it is going to precess at a frequency that differs from this precessional frequency, omega naught. And there's no resonance, therefore there is no efficient transfer of energy, and there is no flip or rotation of that magnetization. So when we measure the signal that we sample is whatever signal happens to be in the bore of the scanner near our coil. But in order to actually generate any signal, right, signal is net transverse magnetization. The spins have to have undergone this flip of their magnetization. That's only going to occur if there was resonance between the precessional frequency of those spins and the RF at the time that we turned the RF on. Okay? So only the spins that lie exactly at isocenter are going to be rotated into the transverse plane. And by the same token, any spins along this plane at isocenter will be rotated into the transverse plane. We'll have net transverse magnetization, which we can detect as signal. Anything on either side, they're just sitting around at rest. Right? So in choosing the correct frequency, right, in the presence of this gradient magnetic field, we can essentially select a slice. Now notice that when we turn on this RF, it's equally applied to the entire body. It's not, unlike CT, right, where you collimate the beam into a thin slice that goes through the patient. In MR, when we apply this RF, which is going to generate our signal, it's equally applied to the entire volume of tissue inside the scanner, or at least inside the coil that's applying that RF. The only way that we can select a slice is by manipulating the frequencies of the tissue so that the match and resonance between the frequency of the RF and the precessional frequency of the tissue only occurs within a specific plane. Okay? Now, this allows us to select a slice at the isocenter of the scanner. So you might look at this and say, well, in that case, if I'm interested in imaging at some other location, right, let's say in the neck, what do I have to do? We could move the patient, right? So we could take the patient and slide him down so that his neck is at isocenter and do the same thing. Sounds kind of like a CT scanner. The patient just progressively moves through the scanner. That's generally not what happens, right? Unlike CT, where if you ever go and observe a patient having a CAT scan, they lie on the table, and the table moves through the CT gantry as they essentially get, sliced up like a bread slicer. In MR, You put them on the bed slides into place, and all the imaging takes place without the patient ever moving. Now, if you're talking about imaging the abdomen or the chest or the head, large discrepancies in territory, I think Victoria asked about this yesterday, you would move the table to get the basic body part in position. But in terms of multiple slices within a certain anatomical region, we do all that imaging without moving the patient. So how can you do that? How could we select a different slice? Someone was going to...
Change the frequency.
Exactly. So the frequency of precession in the presence of the gradient magnetic field is omega naught at isocenter, but it varies continuously as we move in this craniocaudal direction. Okay? And it moves in a predictable linear fashion. So if we turn on our gradient magnetic field with a fixed strength, you know what that strength is based on how much current you dump into those gradient coils. We can predict what the precessional frequency will be at each location along the dimension of the gradient magnetic field because we know what the gradient magnetic field strength is. And by simply choosing a frequency, right, that matches that location, we can apply our RF at this frequency and excite the spins in a plane at this location. So simply by adjusting the frequency at which we transmit the RF, we're now able to select a slice essentially anywhere along this dimension. Now, in this example, using this gradient magnetic field, we're able to select an axial or a transverse slice, something perpendicular to the long axis of the body, anywhere along this head-to-foot dimension. As many of you know, right, one of the great things about MR as opposed to CT is that we have the ability to image the patient in many different planes. So we're not limited to looking at the patient in the axial plane. Well, what if I was interested in looking at, let's say, the liver, and I wanted to do coronal imaging of the liver? So how could we do that? We do it all the time.
Turn the patient on their side.
Okay, well, to do coronal imaging, you would have to actually turn the patient so they were transverse to the bore of the scanner, which is why you can't really do that kind of direct coronal scanning in CT, and you rely on reformatting the images. Right? In what way? Well, this gradient magnetic field can only create a linear gradient in this direction. So it's not, you can't change this gradient magnetic field. But remember yesterday that we discussed that there are 3 orthogonal gradient magnetic fields, right? Any scanner you buy without paying anything extra, you will always get 3 orthogonal gradient magnetic fields. One in the z direction, one in what's typically called the x direction, left, right, and one in the y direction, top to bottom. So if I was interested in a coronal slice, I would turn on not this z gradient, but I would turn on the y gradient magnetic field, which if I was lying back in the scanner would be going floor to ceiling. My slices are now selected perpendicular to that gradient magnetic field, and that would give me the coronal slices I was interested in. Right? If you're doing the spine and you want a sagittal image, what would you do? You would simply turn on the x gradient magnetic field going right to left, which would select slices perpendicular to its direction. And as many of you know, right, when you look at the lumbar spine, we always want these slices that go parallel to the disc spaces at different oblique angles. So having axial, coronal, or sagittal really isn't sufficient for what we want to do. And there's no reason why we're limited to that. In order to generate this type of oblique, you simply have to turn on more than one of these gradient magnetic fields. Right? The direction of slice selection, the key point to keep in mind, will always be perpendicular to the direction of the net gradient magnetic field. Okay? So if I turn on my z and my x gradient magnetic fields, those are magnetic fields, they're vectors, And those vectors can be summed together to give me some net oblique gradient magnetic field. And with the x and z gradients on, I'll have some oblique that will give me slices that are cutting through on a diagonal.
So if you change the relative magnitude of those, you can do
Exactly. And if you want to change the orientation of that oblique, it's simply the actual net gradient is simply a vector sum of its components. So anytime you add vectors together, right, it's the relative magnitude, right, as Karen said, that gives you the orientation of the net gradient magnetic field. Similarly, you can have any compound oblique simply by using some combination of these three gradient magnetic fields. This becomes extremely important, for example, in fetal imaging. Right? Regular postnatal patients are great because you can lay them on the table, position them carefully, slide them in. They hold still or they're strapped down or under anesthesia or whatever. And imaging them in these sort of orthogonal coronal, sagittal, and axial planes is easy. But when you image a fetus, especially one that is young enough to still be moving around, it's totally unpredictable. And the ability to image essentially in any plane is what allows you to generate images that are what we expect in terms of sagittal, axial, and coronal images relative to the position of the fetus. So you need to employ all of those gradient magnetic fields. Now, if you actually go and sit down at the scanner to set up your scan, what you will get is an image, right, after you acquire an image. The scanner will allow you to then take a bunch of lines in this graphical user interface and drag them across the scout image you've obtained, for example, and basically just position them in whatever way you want. So you as the user don't actually have to go in and specify things like turn on these 1, 2, or 3 gradient magnetic fields at these specific strengths. Right? Those computations are all done for you automatically. But that is what's going on when you position these slices. And there can be limitations in terms of how steep an oblique angle, for example, you can generate. Because, as we just discussed, the orientation of that oblique depends on the difference in magnitude of the component magnetic fields. And generating certain very steep oblique gradient magnetic fields may demand that you put a tremendous, perhaps unacceptable amount of power into one of those gradient magnetic fields. So depending on the scanner and depending on the quality and performance of the gradients you have, you may run into a situation where you try and set up some complex oblique image and it tells you you can't do that. The likely reason why you would be told that you can't do that is because of this limitation on gradient power. So far, we've been able to select a slice, to position that slice, and to orient that slice. Okay? If we go back to this diagram, where we talked about the slice being a two-dimensional array of little 3D volumes of tissue. Okay? So these voxels have 3 dimensions. They have 2 dimensions in the plane of the slice, and they have a 3rd dimension through the thickness of the slice. What is it that determines that slice thickness? Right. In our first example, where we transmitted our RF at the Larmor frequency in the presence of this Z gradient magnetic field, we said that we select the spins that are at isocenter. That sounds to me like the spins which are precessing at exactly the same frequency as the transmitted RF, right, lined up along some plane at isocenter, are the ones that are going to be excited, tipped into the transverse plane, and are going to generate our detectable signal. Okay? Now, in reality, when you sit down and set up your scan, you'll have to tell the orientation of those slices, how many slices you're going to have, And you'll also have to say something about the slice thickness. So how is it that we can modulate the thickness of the slice? In this example, is this a 1 millimeter thick slice? Is it a 10 millimeter thick slice? Somewhere in between? More or less? How do you do that?
Varying ranges. Yeah. Each of those that are not exactly in.
Okay.
Are you going to measure?
So first, you have to realize that when we transmit this RF, we talk about, in this case, in this example, transmitting at the low mark frequency. But the reality is that we are always transmitting some range of frequencies. It's simply not possible. It would just be an unattainable engineering feat for us to generate an RF, which is essentially just a loop of wire with an alternating current running through it, as we discussed yesterday, that oscillates at precisely a single frequency. There's no such thing. It is always going to be some tolerance, some range of frequencies. And in fact, that range of frequencies is a parameter that we can modify. So the amplifier that generates this RF pulse actually generates some range of frequencies. The greater the range of frequencies that we transmit, the greater the extent of tissue at which we will find spins precessing at frequencies which match the range of frequencies transmitted by that RF. So by simply changing the width of the range of frequencies that we transmit our RF or B1, we can determine the slice. Okay? Now, there are limitations on the extent to which we can sort of super tune this RF. Right? We can tune it down to these are pretty high performance amplifiers, but there is a limit to how narrow a range of frequencies we can transmit. In fact, that limitation is such that under the example I've set up here, we might really not be able to select a very thin slice. So is there something else that we could do besides modify that range of frequencies that would help us to modulate the thickness of the slice? I'm sorry, speak up.
Can you modify the angle of the gradient magnetic field?
The angle of the gradient magnetic field.
Like if you
Okay.
stick in that angle but you keep the range the same, then...
So I just want to, this may be semantics, but not angle, because angle to me means the orientation of the gradient magnetic field, which would mean perhaps turning on multiple gradient magnetic fields. But I think what you're meaning to say is that we could change what we typically call the strength, or we might call the slope of that gradient magnetic field. So we can go from green to purple here simply by dumping more current into those gradient magnetic fields. Simply by making them stronger at each end, we will have a more rapid change in gradient magnetic field strength as we go from head to toe. Well, what happens in that case? In that case, if we think about some range of magnetic field strength, right? And of course, that range of magnetic field strength is going to correspond to a range of precessional frequencies. So under our green gradient, which has a lower amplitude or a shallower slope, we are going to be selecting this range of tissue, right? The slice thickness will be demarcated by these little orange marks here, because the field strength corresponds to those locations in the scanner. Right? The spins within this swath of tissue are precessing at a given range of frequencies, which let's say is the range of frequencies at which we're transmitting our RF. If we leave everything the same, transmit the same range of frequencies, but ratchet up the slope of this gradient magnetic field, all of a sudden, the range of locations across which we have the same range of field strength and therefore frequency becomes much narrower. So by increasing the slope of the gradient magnetic field, everything else staying the same, not having to do anything with the range of frequencies that we transmit our RF at, we can narrow the slice thickness. And of course, if you flatten out that gradient magnetic field, you can do the opposite. Okay, so this really finishes off our ability to have full control over excitation of a slice. We've been able to, first of all, just select a slice, identify its position along the gradient magnetic field, change its orientation by applying different combinations of multiple gradient magnetic fields, right? And finally, adjust the thickness based on either the range of frequencies that we transmit or the amplitude or slope of the gradient that we apply. Any questions about this?
When you change the strength of the gradients, does the isocenter compared to the green and purple line change?
No.
It stays the same.
Sorry if I didn't draw it accurately to scale. The isocenter is always the isocenter. So the gradient magnetic field is simply changing its slope, pivoting around the isocenter. The isocenter never changes.
Do you ever change the field strength of one gradient with respect to another to change the isocenter?
Okay, so that's a good question. So the assumption is here that as we change this gradient magnetic field, we're putting the same amount of power into each side. And we either increase them both or we decrease them both. But we never only adjust one of them. That's what we call a symmetric gradient magnetic field. And for our purposes, okay, all of the gradient magnetic fields that you're ever likely to deal with are going to be symmetric gradient magnetic fields. That being said, it is possible to generate an asymmetric gradient magnetic field, as you described, simply by putting an asymmetric amount of power into each end of the gradient. But that's not something we're going to deal with at all. And really, I mean, certainly in clinical and most human applications, it really doesn't have a role. So isocenter is always going to remain where it is. Okay. The slice position, of course, as we said, does not have to remain at isocenter. That can be adjusted simply based on the frequency that we transmit. Okay. And of course, if you would generate an asymmetric gradient magnetic field, you would need to account for that in how you tune your RF to select the correct slices. Yes?
Can I ask a question about slice selection?
Yes.
In the examples you've done, you've always selected a vertical slab that we've been working with.
What do you mean by
slice.
vertical?
Well, like up and down within the bore of the magnet.
You mean an axial slice?
Yeah.
Right.
So, and we're talking about transverse magnetization, perpendicular to the B0. Now, if you take a coronal slice in the patient,
Sure.
do you have to excite the entire body of the patient, or does it matter? I guess
What do
it
you mean
matters.
by the entire body of the patient?
I mean, the entire.
Because if you
like,
excite if you excite a coronal slice, that's using a gradient magnetic field that goes anterior to posterior relative to the patient for slice selection.
Okay, so does it matter that
And
the
it's-
transverse? I mean, does the direction of the transverse magnetization within the slice have to do with the angle of the slice at all?
No,
It doesn't matter.
no.
Okay, that's what I'm getting
No.
at, I guess.